Indian Statistical Institute. His research interests are in quantum.
So Debasmita will continue with the Qiskit tutorial. She will show you how to actually create these circuits, how to measure and see these probabilities and all of those things. So Debasmita Bhoumik is a research fellow at the Indian Statistical Institute, Kolkata. Her research interests are in quantum computing and machine learning. She is currently working on the application of machine learning in quantum computing. She did her BSc in computer science honors in Bethune College, and she is a gold medalist from her college. She obtained her BTech and MTech in computer science from the University of Calcutta. So, on to you, Debasmita.
Thank you, Ritujit. Is my screen visible?
Yes, it is visible.
Okay. So we have learned basically the theory part, the mathematical part behind quantum computing. Now we'll see it in terms of the eyes of a computer scientist. That is, we will just go into the programming part. For programming, we have already asked you all to install Qiskit in your machine, or if you don't install Qiskit in your machine, then you can do it in the IBM Quantum Lab, which is open source. So you have to open your account and then you can use their lab where you can do the Qiskit program. And here the syntax is just like Python. So you have to know a little bit of Python to run these codes. And here we will basically see what you have all learned in your lecture, the theory things, and we will see how the circuits are made, how the qubits are measured, and all those basic things. If anyone has previous exposure in Qiskit or quantum computing, this hands-on session may seem boring, but this is for the beginners. So at first, we have to import some libraries, some Qiskit libraries. In the Qiskit libraries, the functions are already written. We have to import those libraries. One thing I would like to mention at the beginning that all those things, all those I am going to show here, most of the things are available and nicely written in the Qiskit textbook. So please follow the Qiskit textbook once this session is over, and I will share this uh, Python file or Qiskit notebook with you all in Discord. So no worry with that. So first we import the libraries, and then first let's see what how a qubit is represented in Qiskit. So we have already seen a qubit that can be 0, that can be 1, that can be in a superposition of 0 and 1. And we have already known about the gates like the X gate, Y gate, Z gate, and there are some other gates. We will learn this in the following week. So first consider let's the X gate, which is like a quantum NOT gate. In original classical NOT gate, 0 becomes 1, 1 becomes 0. So how this happens in quantum? So I think you have already seen this picture in your previous tutorial. So this is a Blochspian notation where the qubit is currently in the 0 state. So how do we write this in Qiskit programming language? We have defined a function. You can give any function name here. We have defined a function where we we initialize a quantum circuit. This is a function already written in the Qiskit library. This function quantum circuit bracket 1 means 1 qubit. So we have created 1 qubit, and all qubits are by default initialized with 0. So we have created 1 qubit which is initialized with 0, and we take that in QC and we return that QC. So this is our function to create one single qubit which is initialized at 0, and then this is the syntax so that we can see this block sphere notation. So you will learn in detail about the state vector notations and block sphere notations in the later week. But currently we can just consider this sphere. This is the x-axis, y-axis, and here this is the qubit 0. Now we want this qubit 0 will become qubit 1. So this pink arrow will get rotated towards this 1. So we will perform a NOT gate, or you can say a bit flip operation. So for bit flip operation, we have taken the same programming, the same code like previous, but we have inserted an X gate here. So QC.X bracket 0 means on the 0th qubit, there is only one qubit here. So on the 0th qubit, we have performed an X gate. And then we do the same things, and we can see the pink arrow is now downwards. So there is a rotation which makes this state 0 to state 1. So this is our X gate, our first gate. Now we'd like to create a superposition. You have all learned about superposition. That is, these qubits are either 0 or 1. Now we would like to see the power of quantum computer, that is superposition of 0 and 1. So you have seen this state, the plus state, which is a superposition, equal superposition of 0 and 1. That is with 50% probability it can be 0, with 50% probability it can be 1 if you measure this. So how to create this kind of state, the plus state? So again, we take a single bit, a single qubit with a quantum circuit with parameter 1. So you created a bit, and this qubit is initialized to 0 by default. Now we put the Hadamard gate, and the Hadamard gate, this QC dot H bracket 0. So for NOT gate, we have written dot X. For Hadamard gate, you have written dot H. And all things are same. And you can see that 0 was the upward direction, and now this superposition. So it is somewhere between 0 and 1. Okay. So now let's combine the NOT gate or the bit flip with this Hadamard gate. So we are combining these two gates and see what happens. So if we combine these two, we get the state minus, the minus state. So previously we have seen the plus state. We have already seen the 0 state, the 1 state, the plus state. Now this is the state minus. This is 1 by root 2, 0 minus 1. The circuit will be exactly same as before, but we will include the Y gate here. So if you just go to the first portion, it is noted that QC dot X is basically rotation by pi around the X axis. So rotation 180 degree around the X axis. What happens? 0 and their 180 degree rotation. This is 1. So this is rotation by 180 degree around the X axis. Here is your X axis. Is my mouse pointer visible? Is my mouse pointer visible?
Yes, it is visible.
Okay. Okay. So this is the x-axis, and you basically rotate pi or 180 degree, and you get the bit flip or X gate. So Y gate is basically rotation by pi around the Y-axis. Now this is your Y-axis. So you rotate the state around this Y-axis. This is the Y gate. So if we apply the Y gate after the Hadamard gate, then it gives us the minus state. And you can see this from the blocks view. So it was plus, this is the plus, we rotate it around the y-axis and we get this minus. Finally, we can move to the complex numbers, because quantum qubits deals with complex numbers. So let's see one example where we are dealing with complex numbers. So we want to make the state minus I. So after plus state, minus state, we are currently dealing with minus I state, which is 1 by root 2, 0 minus I 1. For this, we need the SDG gate. Now, what is SDG? It is S dagger. So S gate is basically rotating pi by 2 around the Z axis. So around the Z axis, we rotate with an angle of 90 degree. Now, if we rotate by an angle of minus 90 degree, that is in the reverse direction, then we get the S dagger. Now, what is the Z axis? This is the Z axis, X, Y, and Z axis. So, for the complex number situation, we basically perform a rotation around Z axis with 90 degree. So here we get the minus ix in the blocks view. Now these were all about single qubit gates. You have already seen two qubits gates. The most basic one is the CNOT gate. CNOT gate is the control node. As you have seen, there are a control qubit and target qubit. And what it does, if you just remember, if a bit is 0, if a qubit is 0, and if the control qubit is also 0, then it does nothing. If a bit is 1, a qubit is 1, the control qubit is 0, then it also does nothing. Now, if the control qubit is 1, then it acts like a NOT gate. That's why it is a control NOT gate. So, if the control qubit is 1, then it takes the target qubit from 0 to 1 or 1 to 6. This is the work of controlled CNOT gate. Now let us, if it is a 2 qubit circuit, now let's design how we can make a 2 qubit circuit. So we have taken a QC quantum circuit. Previously during the 1 qubit circuits, I would like to mention one thing here is there are various syntax of creating the quantum circuits. You can go through all of them in your Qiskit text. Here I am showing just one, that is you take a quantum circuits, you don't give any parameter here, and you want to initialize with 2 qubits and 2 classical bits. So next you initialize some quantum registers. So 2 quantam registers, call them qreg. These are the labels for better understanding, better visuality, and 2 classical register C. So here you can see 2 quantum lines and 2 classical lines here. And then you see dot add registers, these QRs. So these Q regs are added into quantum circuit. And if you add register CR, then these classical registers are also added into the quantum circuit and you draw it. So this is basically a blank circuit kind of thing. We have not operated any gate, have not done any measurement or anything. This is the blank circuit. Now let's put a CNOT gate. So we have put a CNOT gate. If you see the diagram, this is the control, this is the target. So the syntax is qc.cx. First we write the control ur.0. Why 0? Because this is the 0th qubit, this line. The target is QR1. This is the first qubit. This is the 0th qubit. This is the first qubit. This is the control. This is the target. And if we draw, then we can see the CNOT gate. Now we have to measure, because for a complete circuit we are going to measure the we have to insert the measurements. So for measuring, if you want to measure the first line, that is q register 0, you will write qc dot measure qr0. And for measuring like this, you have to incorporate one classical register, because after measuring the quantum states are getting collapsed into classical states, right? So you need one classical bit also. So here 0. And for this another quantum bit, you will also measure using another QR, another classical register, and then you draw. The outcome of the qubits, what will happen, we will see in the next cell. So suppose we have a quantum circuit with a single qubit quantum resistor 1. We have taken a single qubit, and the single qubit is always initialized to 0. And then we take one classical register for measuring. Then we add the registers, and then finally we measure. There is only one classical bit, one quantum bit we measure. Then how to see what happens after measurement? Now, a classical computer, I am running this in my laptop. This is a classical computer and it can't basically measure, right? So for measuring properly, we are using some simulators, which is not basically a proper quantum computer, but it can simulate most of the results of a quantum computer. Here we are using the chasm simulator. In Qiskit, there is the chasm simulator. We have chosen it, and the syntax you can see aer.getBackend chasm simulators. This is our backend. Now counts. As this is a probabilistic event, we have to do this again and again. How many times? You can give them in shots. So we run these simulations again and again. We measure this again and again and then see what is the outcome. Now you can think about one thing, that is, you have a qubit, you measure it once, it get collapsed. Then why should you measure it again and again? Here the simulator does what? That it freshly creates the circuit again and again and measure each of the circuits. This is the work of the Kazam simulator. So here we measure it 1,000 times and then plot histogram means we see what is the outcome of each of the times. So you can see 1,000 times it becomes zero. So our circuit qubit was initialized to zero. If we measure it, we are getting zero because this is not a superposition state. We initialize it to zero and we measure and get a classical zero as many times as you want. Now let's input a bit flip or X gate here. So here we take the same circuit and inserts an X gate to the first qubit. You have already seen how to insert. We will measure now. So after measuring, what happens? Let's see. We have run the same code, and now for 1,000 times we are getting one. So this is how we measure and see what is the outcome of our quantum circuit in Qiskit. Now let's see how you create the Bell state. In the last part of the lecture, we have seen the Bell state. Now we will see how the Bell state is created. Before that, till now, is there any question, Rituchit?
No, not something very
Okay.
important, I
Okay.
think.
Okay. So for the Bell state, as you have seen, it is 1 by root 2, 0, 1 plus 1, 0. And you have also seen this circuit in Ritojit's slide. So how to design this? So there are two qubits as you can see. So we can take quantum circuit bracket 2 for two qubits. Now you have to input an Hadamard gate in the first qubit and an bit flip or X gate in the second qubit. So the first qubit is Q0, the second qubit is Q1. So QX, QC dot X 1 for the second qubit, QC.H0 Hadamard gate in the first qubit, and then you will do the C0 operation. So for the C0 operation, the first qubit, the zeroth qubit is the control, and the first qubit is the target. And then you can draw the circuit. Now, how to measure? There is another way to measure. Previously, we have created the classical lines and measure by fixing which qubit will be measured by which classical line. But there is one more function in Qiskit that is called measure all. By this, we don't have to explicitly fix the classical lines. If you say QC dot measure all, it will measure everything and it will give us the outputs. The rest of the codes are just same, and we can see the outputs. So what is the output? Our target was 0 1 plus 1 0. So half of the time you should get 0 1 and half of the time you should get 1 0. And this is what we see from here. Half of the time we are getting 0 1 and half of the time we are getting 1 0. And why not perfectly half, like it is not zero point 0.5 and zero point 0.5 because this is something probabilistic. If you increase these shots more and more, and if you take this to infinite, then ideally you should get zero point 0.5 and zero point 0.5. And if the shots is very less, then you can get very different output from this. So just keep your shots in something good so that you can get a proper output, like 50%. And one thing is, as you can see from the histogram, the outputs are 0 and 1 0. So the states of the qubits in a Bell state are perfectly anti-codal. Now, Qiskit tends to use the circuit identities to optimize the circuit. Okay, so optimizing means uh, it is also visually optimizing and optimizing in its task also. So if we have a circuit, there are many X gates then it happens that Qiskit will remove the x gate. So suppose there are two x gate. What happens in x gate? It converts 0 to 1 and 1 to 0. So if we put two x gate, it means nothing. It will keep 0 to 0. It is identity basically 0 to 0, 1 to 1, and Qiskit will remove the gates for our in qc.draw for our visual purpose. And it may create some confusion when we draw something. So we can use the barriers. If we give the barriers, then Qiskit will not remove these X gates and combining them into one identity. So this may be helpful in drawing circuits in future. So here we have taken many X gates, and for barrier we have to put QC dot barrier, and you can see this great kind of line. This doesn't do any work, this basically for better visually. The next thing is you can define your own unitary gates. So you have seen gates, you have seen C naught gates, how the C naught gate works, how the H gate, how the X gate works. You can define your own matrix. So for the own matrix, first you need the numpy. You have to import the numpy, and you define a matrix. So here the matrix you can see we have written a matrix, and then we called it a swap. So to use this matrix as a gate, what we need to do that our circuit name is now QC1. So QC1 dot unitary. Then this is a function. Now in a bracket, we basically pass this swap matrix inside qi dot operator, so that this swap matrix can be operated on your quantum circuit. So here you can see if we draw, this swap is basically acting like a black box which we have defined in our code. So thus we can define our own unitary gates also. And here we can use the control. So control swap. So control swap QC1 dot control. You can fix the control, you can fix the target, and all those stuff. Now let's come to quantum entanglement. You have already seen the theory. Now how to see this? You have already seen this in I mean when you are dealing with the Bell circuit, but in quantum entanglement, what we do, if I just repeat, then we are creating an equal superposition using two qubits, and then we look the measurement outcomes. So as you have seen, we have to put a Hadamard gate for creating null state, then a C naught, and then we have given a barrier and the measurements. And as you have already seen how to count and how to plot histogram, then you can see that it's becoming 0, 0, and 1. The final thing, I think this is the last thing. Okay, no. So looking at the state vector, so from here you can see this is 0, 0, and this is 1, 1. Now I'm not going into the detail of state vector. You will learn more about it in the following lectures, I think. But till now we have run it in QASM simulator, right? Now we can choose the gate backend as state vector simulator. Instead of QASM simulator, we are switching to state vector simulator. Now in the state vector simulator, you can just take the circuit. Similarly, you can choose the Hadamard gate and CNOT gates, and then you can execute. If you execute, then you can just see here what happens. It is showing you the probabilities of the states. So the states you can see some states this is 0. We can see the real part and imaginary part separately, and this is basically 0, 0, 0, 1, 1, 0, 1, 1, and where there is some value it is showing, and the middle parts the 0, 1, 1, 0 there is nothing, so it is showing 0. So in the state vectors you can just see the probability in this form. This is something different. And why do I use the state vector simulator? Because in QASM simulator it is expected to have some statistical error, and the obtained outcome, as you have seen, that it becomes ideal as the shots increases. But using state vector simulator, We don't have need anything like that, and it can give us the exact probability of the circuit. And from this, if we are not sure, then we can print the SB probabilities dict. This is a function which exactly tells us what is the probability of the 0, 0 state and 1, 1 state, which we can see from here also. So for this, we need the SB probabilities dict. Now, initializing qubits to arbitrary state. We have already seen in the theory part that we can initialize qubits to arbitrary state, and in this hands-on, we have seen how to initialize it to 0, and then putting some gates to make it to 1 and all other things. Now, how to initialize it is by default 0. Then how to change it? How to initialize a qubit in any arbitrary state? So here you want the state root 3 by 2 0 plus half 1. So probability of sorry 0 is square of root 3 by 2. So you just write this like this. So np square root 3 by 2 and half. You write the coefficients. Np is for numpy dot square root. So basically we write here root 3 by 2 and half, and then QC dot initialize. Then the circuit, the your state instead of state 0, it will be initialized in root 3 by 2 0 plus half 1. And then we can measure and draw. So if we measure this using the back end, then we can see our desired outcome, that we wanted this to be root 3 by 0 and this to be half, and we can see the desired outcome from here. Now, this is a food for thought for all of you, that suppose we have a maximally entangled state. Now, what is a maximally entangled state? It is a Bell state. So, Bell states are maximally entangled state. Now, let's consider a Bell state and to check the block sphere of a maximally entangled state. So, previously we have seen some block spheres, right? Some arrows. We are seeing it is qubit 0 or qubit 1 or something else. So, what happens if we draw the block sphere of a maximally entangled state? So, you create a maximally entangled state by creating a Bell state, and then we do the block sphere notation, and then we see nothing here. You can try to interpret this, why this is nothing here, and then you can let us know in this spot if you want. Why there is nothing in this picture? Why don't we see any qubit here at all? Okay, so that's all in today's hands-on. Now let's back to Ritojit, and if there is any question, then I can take it. I think there is some time left. Yeah. Hello. Okay, I can't hear anything.
Hello?
Yeah.
Yes, Debasmita.
Hello.
Yes, we can hear you.
Yes, yes, be sure. Okay, I think Ritojit has some issue on his end.
Oh yeah, I was unable to like unmute myself.
Okay.
So yeah, got it. So there were a few questions which kind of I answered on the
Okay.
go, but if there are more questions, uh, feel free to ask.
Yes, and one thing is you can always get back in Discord with any of the questions. I am going to share this Jupyter notebook in Discord. Go through it, run the cells by yourselves, try to modify the cells with different parameters as you wish. Read from Qiskit notebook and then get back to us with questions. We will be happy to answer.
So, if there are no more questions, one thing was that Sahana was asking one question about this composite system and its measurement. So, if it is actually okay with you all, and if Sahana is okay, can we deal with it now, or should we deal with it later?
Yes, it is okay with me. After all, we have time till 8, right?
Yeah.
Yeah.
Okay, so there is one question, ma'am. Why are the basis states 0 and 1 shown as polar opposites? Is it not better to represent them at 90 degrees? So, Debasmita, do you want to take it, or
Okay,
I
okay,
want
let
to?
me share the screen and you can continue. Let me share the screen to both
Yeah,
of
so
you.
while Debasmita is sharing the screen, the block sphere representation and maybe density matrix is something that the speakers tomorrow will cover in a bit more detail, and perhaps then it will be even more clear to you why they are polar opposites and not like 90-degree. But if Debasmita wants to add something.
No, actually, in the block sphere notation, it is like that. You can see that if you do a bit flip operation or the x gate, it rotation by pi around the x-axis. It is the rotation around 180 degree around the x-axis.
So one more thing to add, I mean, these are not like very concrete answers because you haven't gone through density matrix yet. You will go through tomorrow,
Right.
and
Mm.
then hopefully we should be able to provide you a more concrete answer. But so if you remember, like when I talked about this Z basis, and I said that the two eigenstates are 0 and 1, and here if you see the picture Debasmita is showing, okay,
Okay. Yeah.
the picture Debasmita was showing. So this particular axis written 0 in the top, 1 in the bottom, that is the Z axis. So that kind of corresponds to the Z basis with the two eigenstates in the two corners. So I guess that is the concrete way I
Yes,
can go
actually,
to
in this
without,
kind of pictures, we don't see the z-axis, but it is like here. This is the
yeah.
z-axis, x, y, and z. This is a 3D diagram, so this is the z-axis. Is there any question left? Because in this screen, I can't see. If I am sharing the screen, I can't see the question.
No, not yet.
Okay.
So if there are like no more questions to this, is Sahana, are you like here? Okay, I don't think Sahana is here. Then we can take her questions maybe later in Discord. Okay, so if there are no more questions, maybe we can stop for today. And tomorrow we'll again meet at 6, and there will be two more speakers tomorrow, and we will learn more about this density matrix thing, what is the block sphere idea, and more on something called super dense coding, and which is kind of an application of this maximally entangled state or Bell state that you have been seeing both in theory and the tutorial.
It's okay. Thank you then.
Uh, so just 1 second. So Ritom is asking like, is it two part, real part, or and complex part? So do you mean the probability amplitude? If yes, then yes, the alpha 0 plus beta thing that I was showing, alpha can be complex means that it can have a real or a complex part. So you can have something like say 1 plus I by root 2. So that is a valid probability amplitude. So, and the probability corresponding to it, you always take the modulo square. So it will like the complex part will always go away,
And
and
I
you will
think
have
you
real
can get
probability.
the examples of this in the IPNV file, Pritam.
Yeah, yeah, right. Okay, then I guess good night to you all, and thank you so much, Vishal, for allowing us to use this WebEx. So we'll see you all tomorrow. Then good night.
Yes. Good night. Bye. See you all tomorrow.
So, Ritajit, you can end the webinar if you wish.
Yeah. Yes, yes, yes.
Thank you.
I'm
Thank you
ending
so
it.
much.
Yeah. Okay. Bye.
Bye bye.